to the session Normalization in DBMS to explain mastering in data integrity. Today we will discuss one of the most fundamental concepts in database management systems, normalization. Normalization is a systematic process of organizing data in a database to reduce redundancy and improve data integrity. It ensures that every piece of information is stored only once, making databases more efficient, consistent, and easier to maintain. Imagine maintaining a student database where the student information appears hundreds of times. If the student's phone number changes, every occurrence must be updated. Missing every one record leads to inconsistent information. Normalization solves this problem by structuring data logically. By end of this presentation, you'll understand why normalization is important, the problems caused by poorly designed databases, the normalization forms like first normalization form, second normalization form, third normal form, voice code normal form, higher normal forms such as 4NF and 5NF. Also, we'll discuss the advantages and limitations of normalization. Also, let us go through some practical applications in real-world database design. Normalization is not just a theoretical concept, it forms the foundation of every well-designed relational database. Let us discuss the problem when databases break. So before understanding what is normalization, let's first examine what happens without it. Let us take poorly designed databases which create several types of anomalies. For example, data redundancy is a main problem. The same information is stored repeatedly. For example, in a database, we have three columns, namely student ID, student name, department, where the student IDs stored are 101, 102, and 101. For 101, the student name is Rahul. For 102, the student name is Anita. These two students belong to CSE and EC department, respectively. Here, the Rahul's information appears multiple times. Problems includes it will increase the storage, it will waste the memory, and also maintenance is being difficult. Second problem associated with the databases without normalization is update anomaly. Suppose Rahul changes his department. If Rahul appears in 5 records, all 5 must be updated. If one record remains unchanged, the database becomes inconsistent. Third one is insertion anomaly, where suppose a new department starts but no students have enrolled. Because department details are stored only with students, we cannot insert the department without student information. Fourth one is with deletion anomaly. Suppose the last student in the A department graduates, deleting that student's record also removes the only information about the A department. This leads to unintended data loss. So normalization eliminates all these anomalies. Let us see the objective of normalization. Normalization aims to organize the database tables according to well-defined rules. There are three major goals. One is eliminate duplicate data. That means every piece of information should be stored exactly once. Example, instead of storing customer details in every order, we can do it in a different way. Like in customer table, we can have customer ID and customer name. But in order table, we can restrict with order ID and customer ID alone. Uh, Thereby, the customer name can be accessed with the help of customer ID. This reduces duplication. Second one, to maintain data integrity. Data integrity means information remains accurate and consistent. When customer information changes, only one record needs updating. Third one is improve database scalability. That is, make growth easier. As organizations grow, databases may contain millions of records. The normalized databases require less storage. It supports faster maintenance, reduce errors, improve consistency. Normalization creates a flexible database structure that can easily accommodate future changes. Let us discuss the normalization forms one by one. First normalization form is the foundation of normalization. A table satisfies first normal form if it satisfies the rule atomic values. Each field only contains one value. Let us see one example. The student subjects stored for one student, two subjects stored in one cell. This affects the rule of normalization. So to overcome this, we can replace that in two cells with the student name repeated for both the subject names. Rule 2, there should not be no repeating groups. Like we must avoid columns like phone number 1, phone number 2, phone number 3. Instead, we should create separate rows for handling that. Third rule is unique primary key. Each row must have a unique identifier. For example, student ID uniquely identifies every student. Benefits of one normal form are easier searching, easier updating, and better consistency. However, one normalization form still allows duplicate information. Further normalization is needed. Let us discuss that in upcoming sessions. The second normal form is the one where a table must first satisfy 1NF before moving to 2NF. The 2NF removes partial dependency. Partial dependency occurs when a non-key attribute depends on only part of a composite primary key. For example, the enrollment table is having student ID, course ID, student name, course name, instructor, composite keys such as student ID, course ID. The student name depends only on student ID. The course name depends only on course ID. These are partial dependencies. The solution for this is this table has to split into three tables. For example, students, courses, and enrollment. Now, every attribute depends on the complete primary key. This eliminates partial dependency and thereby achieves second normal form. Benefits of this second normal form are it eliminates redundancy, it reduces update anomalies, and it improves organization. Let us see the example given here. So before second enough, the table order items has order ID, product ID, and quantity. Here, order items table with order ID plus product ID as composite key, but quantity depends only on product ID, which gives partial dependency. So to resolve it, the order item table is actually further processed as two separate tables named as orders where order ID and customer will be there, and order items where order ID, product ID, and quantity will be there with full dependency. Moving on to third normalization form, it removes transitive dependency. The transitive dependency occurs when the primary key tends to non-key attribute and another non-key attribute. So for example, employee ID, employee name, department ID, department name are there in a table. The employee ID determines department ID. The department ID determines the department name. Therefore, employee ID indirectly determines department name. This creates redundancy. The solution for this is the employee table will have employee ID, employee name, department ID, department table, sorry, department ID, and then the department table will have department ID and department name. The benefits of this are it removes indirect dependencies, it improves consistency, it simplifies updates, it prevents duplication, and so on. So let us see this example scenario to understand third normal form. Here, a 2NF table is there. That means it is a prerequisite for third normal form. A table must be in 2NF. So table already in second normal form. Now, a chain is found here, like A determines B, B determines C. This is a chain link. So to overcome this, we're going to split the tables. So the last field will be moved into its own table. That means if point A to B and B points to C, then A indirectly points to C. So the 3NF will put C in a separate table tied to B, thereby overcoming the transitive dependency. Moving on to the Boy's Code normal form. It's an improved version of third normal form. Sometimes a table satisfies 3NF but still contains redundancy. So the BCNF solves this issue. The BCNF goes a step further than 3NF for tables with more than one possible ID. For example, for every data relationship X tends to Y, X must be a master ID. It must point to one exact row. Some 3NF tables still leave duplicate data behind when IDs overlap. So BCNF will help prevent those simple mistakes. So when we have to apply the BCNF, that is, when a table has two or more possible IDs that share the fields, at that time we have to apply for BCNF. For example, if you consider a table where professor, course, classroom are there. Here, every determinant must be a candidate in PCNF. So let us discuss this. Suppose one professor teaches one course. One classroom is assigned to one professor. Multiple candidate keys exist. Such situations may violate BCNF. So solution is split the relation into smaller tables where every determinant becomes a candidate key. The advantages are it removes remaining redundancy, it eliminates hidden anomalies, it produces stronger database. This consistency. This BCNF is widely used in enterprise database systems. Moving on to the higher normal forms 4NF and 5NF, most applications stop at 3NF or BCNF. However, complex systems may require higher normalization. The fourth normalization removes multi-value dependency. For example, employee, skills, languages, etc. are the cells. An employee may know multiple skills and multiple languages independently. Instead of storing every possible combinations, create separate tables like employee skills, employee languages. This reduces unnecessary combinations. This is handled by fourth normal form. Coming to fifth normal form, it deals with joint dependencies. Large tables can sometimes be divided into several small tables. When these tables are joined, the original information should be reconstructed without introducing incorrect data. 5NF is mostly used in banking, healthcare, large ERP systems, scientific databases, etc. Let us see when to stop this trade-off. Normalization offers many advantages. The advantages includes it eliminates redundancy, it saves storage, it simplifies maintenance, it prevents anomalies, etc. However, over-normalization also has disadvantages. The problems include too many tables will be there, complex SQL queries will be there, increased join operations will be used, slower report generation will be there. For OLTP systems, normalization up to 3NF is generally recommended. For data warehouses, controlled denormalization improves analytical performance. Therefore, database designers always balance normalization with performance requirements. Normalization is one of the most important principles in relational database design. It ensures that data is accurate, storage is efficient, it updates remain consistent, the databases scale easily. So the key takeaways from today's session are to start with 1NF, which keeps atomic values and unique records. Moving to 2NF, it removes partial dependencies. 3NF will help us to remove transitive dependencies. The BCNF, which is the stronger version of 3NF. And 4NF and 5NF usually not used for the OLTP systems, but it is for higher normalization forms where 4NF remove multi-value dependency and 5NF remove joint dependency. So a well-normalized database is easier to maintain, less prone to errors, and more adaptable to future growth. While higher normal forms offer greater data integrity, designers should always balance normalization with system performance based on the application's needs. Thank you.